Good morning, everybody. You all had a good weekend. Start with questions on the homework. Hoping there's some as an indication that people have been working on it.
Do you have advice on how to train on one font and test on another when like the characters don't line up or not the same?
Yeah, so that's kind of a tricky issue, right? So we have basically for each data set, right? We have these images, and then they're mapped to the Unicode value, which I'll just write out the ASCII, right? There's way more Unicode values than there are actual characters in our data set, right? So kind of the first step we did was we transformed this A into some index, so maybe say it's 5, right? That way we minimize the number of outputs that we have to have in our network, right? Everybody kind of happy with that. So that's, we'll do the same thing with the char RNN stuff. So yeah, these are going to be different for, well, if the characters are different, and I guess you get unlucky with the ordering, you're going to get different mappings for each font. Yeah, there's a couple things you could do. So if the fonts don't have the same characters in them, right? Any thoughts on what we could do when we're testing and we're training? So if the training set and the testing set have different, maybe the training has an A, the testing has a B, and they don't have the others. So what reasonable things can we do there for evaluating how well our networks work? So like one thing we could do is we could train on the union of, so have our network have an output for the union of all the characters that appear in either, right? So what are the pros and cons of that? So let's say I have, my one font has A, B, C, D in it. My other font has A, B, C, E in it. Okay. If I trained on the union, if I had my model be related to the union of these two fonts, right? What would my output? What outputs would I have? The neurons for? A, B, C, D, E, right? And there's some good stuff, some bad stuff about that approach, right? So what are some things we should consider before we pick this approach?
Training on one, testing on the other, there'll be no understanding of what E is to the training model.
Yeah, so I will see no training examples for E, right? But I will probably test on it, right? So I probably won't do very well on those examples. You never know, but probably won't do very well on those examples, right? So this is probably going to hurt our testing accuracy a little bit, right? When would I definitely want to do this kind of approach? Under what circumstances would this make sense? If for some reason it's really important that I output E's, then this might be what I do. Right? I should probably get better training data, but maybe that's one approach. So this would be the union, or sorry, the union. Okay. What's another way I could deal with these? I could use the intersection. Right, which would be what? Just be ABC, right? And then I can throw out any training or testing examples that don't match this. Yeah. What are some pros and cons of this one? I'm throwing away examples, so I'm going to get rid of some training data and some testing data. Yeah. How about pros? Yeah, I'm testing and training on the same, on reasonable subsets of the data, right? So as long as they mostly overlap, right? I'm like training and testing on the data that I care about, right? So I think this is a pretty reasonable approach. So what I would do for this one is I would find a mapping from the Unicode to an index for the intersection of the two fonts that I care about. Okay, so find out, okay, which characters they have in common, come up with indices for those, throw out any rows that aren't in that union, and then use those indices for my network. So that kind of makes sense. Yeah.
For the Keras network, I've been struggling with the input shape for the convolution layer.
Okay.
What is the correct way to put that in? And like assuming you have 20 by 20 images, for the depth is like the number of samples, if that makes sense.
Yeah. So what I would do is I would look at the digit notebook that we used and look at what the shape of what the X shape is, and then what we put for the input shape there, and try to match that. I don't know off the top of my head, but that's like where I would start looking.
Okay.
Input shape worked for me with 28, 1.
That's what I have. So it must be a separation.
So it could be that the shape of your data is different.
Okay.
So since you're hand creating your input X, so it's important to make sure that it's a single NumPy array of like 3 or 4 dimensions or whatever, and not a list of NumPy arrays.
So I want to check and see.
So that could be it. I think there's a function called Ravel that will help with that.
Okay.
Which is the
Stack also.
Or stack, yeah.
Okay.
Ravel is the opposite of unravel, which I didn't know was a real word until it showed up in some of these array reshaping operations. But yeah, so a stack will also take a list of arrays and turn it into one array. Yeah.
I noticed that when I'm training models, if I train them multiple times or whatnot, they'll have slightly different accuracies or losses at different times. Are the biases set randomly, or?
So the weight initialization is random. So the initial values are random, so the rest of the training will give you different results. I think it also, if you train once and then train again, I think it doesn't reinitialize. So if you don't actually change the model,
Usually it's like I'll restart the whole kernel, and I'll retrain.
So if you like reran train twice, the second time it would start with what you had trained already. So you'd be starting in a better spot too. So that's another.
Even if I restart the kernel?
If you restart the kernel, no. But like if you like reran the same cell, like you'd start off at 80% accuracy. So, but yeah, the weights are initialized randomly. So all the weights on biases. Or the biases might be 0 to start with, but in any case, yeah, the initialization is going to be random. Yeah.
So for the denoising part, I'm trying to recycle the older methods with the reshaping the 20 by 20 by 1 like you had recommended. I'm getting trash right now, and I'm wondering, a lot of the examples from the slides, or the lecture, say 28, 28, 1.
So that was just happened to be what the pictures were in that one.
So
when
we
you
just have
say
to keep finagling.
when you say trash, like when you drew it, was it like too noisy, or you got?
Yeah, it's just like.
Oh, you could adjust how much noise. So you could turn it down a little bit if you.
So it's probably not like how I'm importing the sets. It's just the actual noising.
If it works at all, I would like, if it's not giving you a dimension error, then I would think you're pretty close, but, yeah, and another thing is, if, making sure that the input is scaled properly. So I think the input pixel values are 0 to 255, is that right? And we would ideally like to scale those from 0 to 1, because like the sigmoid and the tanh are going to be in that range. So that might be another look at. I would expect if you were training anything on scale data, you would have a hard time. Yeah.
Just when we're creating the one column for representation, or is that on the index?
Yes. Mm-hmm. So when I say, like, I have this A, character A is index 5, right? And my network, right, I'm going to input my image over here, and then I'm going to go through my network. And then over here I have my output layer. Okay. So if I stick an A in here, right, what do I want the output layer to look like? What should the output be? So it should be 0 for all of the outputs except the one that corresponds to the A, right? And so that's going to be, index 5. Right? We want this to be a 1, and everything else to be a 0. So that's the 1 hop. So the index is basically, right? I have the number of indices outputs, right? And one of those should be turned on, and it should be the one that corresponds to the letter that we have. So to do a prediction, right? I feed in an image, I find the max output, I see what index that's at, I plug that into my mapping between here to figure out which letter it corresponds to. So how many people have successfully trained on one font? Okay, a couple. Did you play around with different fonts at all? Do you see, like, are some fonts easier to train on than others? No, all about the same. So I'm curious to see which fonts people pick for the different training and testing, and how does Comic Sans training data work on Times New Roman testing data, that kind of stuff. All right. Any other questions on that? All right. So today we're gonna do kind of a lab. So we're gonna get some hands-on practice working with some graph data. And I wanted to preface this by going through a kind of a similar example that I was looking at, so we can just kind of talk about process for how you go about doing something like this, and hopefully it'll kind of help you as you go through your own version. So one of the things that we talked about on Thursday was about the various layouts we could use for node link diagrams. Right? So what were some of we talked about kind of 3 possibilities for how we might lay out our nodes. Do you remember what those were? Okay. So one thing we talked about was a free layout where we could position the nodes however we wanted. Right? We could use like springs and magnets or springs and charges to make that happen. So that was one approach. Anybody remember either of the other 2?
There's a lot of Ajax representation.
So that was another completely different approach. If we're sticking with node lengths, dots and lines. So for some data, we don't really have the opportunity to lay them out. Right? So for some data, if there's position data, things might be fixed, which was the example here. I have data on a map, and so the position of my nodes, seems reasonable to put that on a map, and position the nodes where they are geographically. And then the third we talked about was a restricted layout. And the most common example of that is probably the circle layout, where we put stuff on the edge of a circle and then have our edges in the middle. Okay. So I was kind of interested. This particular data set was kind of interesting to me because, there's like this geographical part of it, but also like maybe there's some insight to be gained from organizing the node some other way, right? So, here we have all the length of these cables and stuff is a big part of what we're seeing here. Like maybe there's some other patterns to be learned by laying this out another way. So my goal was to kind of try to figure out what to do about this, and look at how else we could visualize this. So the first thing we need to do is get access to data, right, so that we can actually play with this stuff. And it turns out that this is actually a open source project, and all their data is open source. So they have this cool little GitHub repo with all of their they have all their data here. So there's two data sets. There's the landing points, which are where all these things are, and for each one there's a little JSON file about information. There is and then they also have information for each cable. So this is the cable that is in Alaska somewhere, and it's got landing point IDs to tie this data to the data set. And so I thought, okay, well, I can clone this repo, get all this data, and then we can look at it. So I started by importing the JSON data that they have. And if we look at what's in here, right, so we have for each of the landing points, so this is where the cables connect to the mainland. We have geometry, so where it is in terms of latitude and longitude, and we have an ID number which helps us relate it to the cables and all that stuff. So here's all our landing points. The cables was a little bit more of a pain because each cable is in a separate file, and so I had to look at all of the cable files and load everything separately. So we loaded all this, and then I'm going to build I built my graph out of all this. So I'm using NetworkX, made a graph. I'm going to store all the positions of the landing points so that we can draw them, on like a map. And I'm keeping it separate from the actual node data structure so we can also draw it other ways. That was kind of the idea here. And so for each of the landing points, I'm just looking up in the JSON to get the ID number for the landing point, making a node for it, and with NetworkX you can store attributes. So I'm storing the name along with the node, so if I wanted to use that later I could. And then I'm storing the position in terms of the latitude and longitude. And then for each of the cables, I'm adding an edge to my graph between the first two landing points, the two landing points. So they have the nice ID, and then I'm just keeping track of which ones I've actually put cables between. And pretty quickly, I get a much uglier version of the nice, pretty picture from here. All right. So yeah, we're in business. Cool. Does anybody notice anything, obviously different about? And so there's a ton of differences, but in terms of like the data, is there any weird stuff that stands out to people here?
There are nodes that are unconnected.
Yeah, there's unconnected nodes. And this actually confused me until like an hour ago. Yeah, I thought, okay, well maybe they just have extra landing points. So I was interested, okay, how many nodes do we have? We have 1,100 nodes, and where I have it in here, there's something like 450 cables. So there's 450 cables, 1,000 nodes. So, at the least, 200 to 300 of these nodes are unconnected. Right. Any ideas where I went wrong on that? What the mistake in my logic on this was? Might help to look at. Specifically, maybe we'll look here.
Oh, the endpoints.
Yeah, so I had assumed that my data set was, 2 endpoints, but actually a single cable can have more than 2 landing points, and so this particular cable is a 3-segment cable, and so that's so a whole bunch of these connections are actually missing, and so that's part of the issue there. But alas, I went forward with my visualization. Okay. So from this graph, it's really hard to see any sort of patterns, and so I thought, okay, maybe node link's not the way to go. So for this type of graph data structure, how else might I, go about trying to visualize the connectivity? Node link seemed, cluttered. What are my other options?
The number of connections.
So I could do some sort of like histogram thing to look at, what the average degree is of all these nodes. So that might be interesting. If I want to visualize the whole graph, right, we talked about 3 options. We had the node link. We had containment-based things. Would that work here? The implicit graphs that we talked about. Or implicit, not really graphs. Kind of the hint. So the implicit stuff where we used containment, that didn't work for general graphs. Right? That only worked for trees where we had a hierarchy of things. Right? Here we have loops and all sorts of stuff, so we can't really use containment, which leaves us with our third option. If you remember, is what our third approach was.
The matrix.
Matrix representation. So this is what the matrix representation looks like, and wow, that's maybe not that illuminating. We can see a little bit of a cluster up here, right? It's unclear if these other nodes are part of clusters or not. What would we have to do to kind of be sure about that? If we really wanted to be able to detect clusters, then our matrix representation, what would we have to do?
Make sure that you're ordering.
Yeah, so I'd have to basically find the optimal ordering of my graph so that, things that might be in a cluster are, adjacent in rows and columns, right? Turns out that's really, really hard, and the NetworkX library doesn't really have tools for doing that. So kind of the best we can see is, oh, there's sort of a cluster here, and that's kind of the best we can do. The other thing, so this I thought might be a useful visualization where we're looking at a circular layout of our nodes. And here we suffer from basically the same problem, right? There probably is some more insight to be gained from a picture like this, but what's it going to require? So basically, we're going to need to order the nodes better, right? We want to minimize the number of edges that are going, totally across, probably, right? And what were some of the other techniques that we talked about that would help make this more readable? Bundling, right? So better sorting and bundling, and again, NetworkX doesn't do either of those things. So I had this genius plan to partition the graph, cut it into pieces, and any guesses what, if you were going to break a graph like this into pieces, what pieces might you expect? Yeah, so I was kind of hoping, like, okay, I'm going to do some graph partitioning. I'm going to get like North America, West Coast, East Coast, and and then I can put those nodes together, and then I can do bundling. Unfortunately, the library that does partitioning doesn't compile on Mac OS, so couldn't do that either. So this is big old disappointment about all the things I wanted to do but couldn't. All right, so I have this graph with too much stuff in it. The next thing I thought about was, okay, well, I can simplify this graph by throwing away all the nodes that nobody uses. Here we go. So what I did was I just grabbed the subgraph. So this is all the nodes and edges, but I only included the nodes that were actually connected. Right? So I threw away all of the nodes that weren't connected. And so now if I draw it, right, there's no more lonely nodes, but there's a whole bunch of disconnected components because I probably didn't include the cable information that would have connected them. If I had done the full data set, would we expect there to be a single connected component or multiple pieces? What do you think? Yeah, so it's the internet, right? We're looking at a map of the internet, so hopefully it's connected. So you might think, that's a reasonable argument that it would be, we'd have a single connected component. Otherwise, like, there's some part of the world that is not part of the internet. Should be pretty weird. The argument I have in the other opposite direction is that this is actually not a map of the internet. It is a map of a subset of the internet, which is only the undersea part. So here we're ignoring any cables that go across land. Right? So it could be that there are components that are only connected via land to the other part. So I have no idea whether we expect one connected component or many. If we look at the nicer version, I don't see any, I guess, so this part of Australia here is presumably connected by land to the cables that go all around. So So even if we did have everything, there might still be a bunch of disconnected components. In any case, this graph looks about the same, right? Because the edges are the same. We just removed some of the nodes. And again, we'd need better sorting and better bundling. But the matrix looks, you can see a little bit more in here because we've reduced the number of rows and columns. Still, we need to do some sort of clever sorting in order to and then the last thing I played with to simplify was I removed all of the nodes if to get the more connected part of the graph. So I just threw away any vertices that only had degree 1. Okay. And now we're starting to get to like a reasonably sized amount of data where if I had labels on here, you know, I might be able to gain some insight from this. So, yeah. So this is just kind of an example. Okay, I'm doing some analysis of a real data set. A whole bunch of challenges popped up from the data format being kind of a pain to you know, to the scale of the data kind of being too big for the very simple graph analysis tools that are built in, especially specifically the visualization. So, any questions about that process? And a little bit disappointing where it ended up, but you know, it's a hard problem, so you know, it's not that surprising that things didn't work out perfectly. So the rest of the day, we're going to spend on analyzing another data set. This data set is a dump of the IMDb database, the movie database. And so we're interested in answering some questions about movies that we can learn from this database and trying to understand what's in here. So this is a gigantic JSON-ish file with, I think it's over 100,000 movies from all over the world. Okay? And we want to look at North American movies because we're going to be Anglo-centric tonight, or this morning. And so we're interested in knowing, okay, which actor has been in the most movies? The very important question, is the 6 degrees of separation from Kevin Bacon true? Okay. And if not, who's not doing this? And then we also want to know if the 6 degrees of Star Wars is true. Okay. So we're going to try to play the same game, but instead of looking at connections between actors, we're going to look at connections between movies and see what we find. Okay. And then we're going to do just a little bit of visualization. Don't try to graph the whole database. It will hang Python really fast because it's a very large data set. Okay. And then we're going to look at PageRank and have one open-ended bit here. So find something else interesting about this data set. Okay. So yeah, that's the plan for the rest of the day. There's a bunch of things that are pretty tricky. I'm going to kind of let you struggle against some of the stuff that comes up, and we'll kind of chat at a few moments to see how people solve various problems, and we'll go from there. So that's the plan for the rest of the day. Any questions?
There's a JSON file.
Oh, did I did that.
Says it's forbidden.
Hmm. Yeah.
It's in there, it's just under the.
It should-
It is folder.
Yeah. And that's,
Yeah, I go.
you can't download it?
Extra.
Oh, I see. You might have to go to GitHub and click download to get it.
So it's there, it's just giving it error. Try to load it.
Yeah.
Even if you go through the GitHub website?
No,
Yeah.
I'm trying to import it into.
You know, but
So Jupyter says that there's an unexpected non-white space character after the JSON data.
Oh, yeah, yep. It's bad JSON. So, cool. Yep, that's the first, so yeah, look at it. So you're trying to use like JSON.load on it? Yep, yeah. So take a look at it, and you got this data, it's a format that said .json, but yeah, it doesn't really look like, or it only resembles JSON.
It's really just like a bunch of bullshit. It's like. So instead of. JSON off of-
The demo will take a while, like 70 minutes.
Just to load before, like,
Yeah.
I probably should have it.
This is also a good stress test for whatever editors or viewers you're using. So, like, if you're using an editor that tries to open the whole file at once, tries to like syntax highlighted, it might show really bad. And it's like you're working on a text editor and something like that, and you want to test it.
Yeah, all this. Poor girl.
I don't have to. I'll just. Your boss is up to see it. He's all
If it's not correct JSON format, do we want to keep it or do we try and fix it or just like move on?
So it probably depends a little bit. I would say, so the first thing I would do is figure out which things aren't good JSON.
Okay. So look for commonalities.
And then see like, okay, well, is it data that I actually care about or not? So what have people found out about this data that we have here? So what are some things that people noticed? It's stupid and it sucks. Yep. It's actually kind of amazing how much, like, this is an absurd treasure trove of data. It's like has the actor, directors, and plot for 100,000 movies. So that's actually kind of cool. So in terms of formatting, what's cool about it? What sucks about it? So it's one movie per line. Is that a cool thing or a dumb thing? That's a cool thing. That's extremely helpful. Yeah. What else?
Like having a plot kind of sucks. That might just be.
It's kind of noisy. There's more stuff that you care about, right? There's the meta score, a link to the poster image. Not all that helpful, but it's in there. The movies on the lines. Are they generally good JSON format? Who's tried to like parse the JSON? Cool. So if you just throw the file at it, does it work?
No.
Nope. And why not?
I get it working, but I think it needs to be in array.
Yeah, so a JSON file has to be like one object, and here we have 100,000 objects, or we have an object, an object, an object, and this is like not valid JavaScript. There's no separation between them. Yeah. But if you look at an individual one of these, is that valid JSON? Cool.
Yeah.
So what strategies on how we might go about loading our data? Just line by line with JSON. So that's way smarter than what I did. My first thought is, oh, that's not valid JSON. So I'm going to turn it into valid JSON. How would you go about turning it into valid JSON?
So if you put a square bracket at the beginning and a square bracket at the end and a comma at the end of
Yeah.
those braces.
So that's actually exactly what I did. Started with, I read each line. I put a square bracket at the front. I put a comma and a new line between each line, and then I put a square bracket at the end. This actually made my life a lot harder than just reading it line by line to begin with. And here's why. So there's at least one movie that is not valid JSON in here. Reading it, if you make one gigantic JSON thing, turns out that Python's JSON parser there's really bad error reporting. It tells you like the line number, but it's like not quite a line. So figuring out where the errors were was way harder. But doing it one at a time, right, it's pretty obvious where the errors are, and you can kind of track that. So, right. So that's, I think, kind of the first challenge of dealing with this data set is how do I load this almost JSON? I think, yeah, you guys jumped to the better solution than me almost immediately. So, yeah. Who's found the broken movie entry? What movie was it?
This is legend. There's a single slash that should be there. I'm moving it.
This one.
Yeah, it's at the end of the plot. There was an extra slash afterwards one last time.
Is it a motion or a point? I don't think that's there. This lowercase o. Let's see. But yeah, in any case, there's one that somebody threw a backslash in front of a quote, and everything broke. So yep, we got a huge data set. Fortunately, there's only one of those in there, but yeah, big data, right? There's one errant backslash, and then, again, screws everything up. Going through line by line, it's going to be way easier to find that than if you were dumb like me, but yeah, still a pain. Do we care about that entry? No, why not? Maybe it's a very important entry. For the analysis that we're doing, it specifically doesn't matter.
Oh.
Yeah, it's not a North American movie, so throw it out. Which brings me to the next challenge. How do we find movies from North America? So we have a country field, right? So country, Hong Kong, cool. So we could just look for a country. I don't know what's an American movie I can look for really quick.
All the steps out.
We'll go with one I know about. Okay, so Big Lebowski, cool. Country, USA. So if I just search for country USA, is that going to work? Maybe, maybe not. Yeah, most of the. I don't know if America's in here. Let's see. I'm using ag, which is it's grep. It's just a faster version of grep. So I don't see country American here. So it looks like USA is definitely the way. Is definitely the indicator. But as we saw. So the first one, the kind of the test movie I looked at was the Lord of the Rings stuff. And if you look here, it even puts New Zealand first. So how are we going to get the American movies out? We could use the regex. What would the regex look for? We could look for USA, but we want to make sure that it's only in the country part.
Save the country and then look in the country.
Yeah, so fortunately we don't have to go straight to regex because it's JSON, so there's more structure. We can grab the country part. But how can we tell if USA is part of? So we could just search for USA in there. Another trick that I like to use for these formatted lists is to split on comma space. So if you split a string on comma space, it basically unformats the array and gives you back the list that it's made it. So if I take country and split on comma space, I'll get New Zealand, USA, and then I can check to see if USA is in one of those. So that's how we can figure out what our North American movies are. We could use a regex. We'd have to be kind of clever because we want to make sure that it's in between the quotes of country, and it's a little bit tricky to make sure that we get like in those quotes. But yeah, we could do that as well. But since it's JSON, it's a little bit easier. This is the kind of thing that I think list comprehensions are pretty handy for, to like select a subset of data. So you might play with one of those. It should be fine, except that you'll miss things like where
So if you could tell,
yeah, anything where USA is one of the countries. So that's syntactically it. I would put it like into a list. Yeah, so make an empty list to start looking at that.
Are we safe to say all caps USA or?
I think so. Yeah, they are very consistent about most of the formatting stuff. So I think all caps. If you wanted to do lowercase, that should be pretty easy.
Sorry, I just got this. Are we, is that like a specific, so it's this library? Oh. Are we using?
I would build the graph with like that.
So we don't actually go with
No, it's not in a structured graph format. So we have to build that.
Oh, and then.
So yeah, you have to take the JSON objects.
USA.
But obviously not as much as what most people in Jersey do. Let's see this portion or this one. Or come this. Just, I try to give them images.
So the JavaScript is going to take a string and turn it into, or it's going to take an object and give you the JSON back. And what is the data that you're doing?
So the data just.
So what you have is an array. So your JSON object is an array. So to look at a particular movie, you can use a pointer.
Obviously, just do it.
Yeah, just list the JSON objects is fine, I think.
Oh.
Like you're not really going to get it. That's when you dump it and reload it, it's going to be basically exactly that. I think, so yeah, I think what you had was fine.
Okay,
But you just don't have like a key to look into it.
Okay, I feel like this better than that.
Yeah, I don't think you need to look up a key into that stuff, right? When you want to do the query stuff, you're going to want to do that interactive stuff.
Okay.
Yeah, so some of them are like NA or have like a root all those lines.
So what we don't.
Right, because some of them are like this. It's just a font. Some of them say.
Yeah, there's a JSON library, or like, and so you can parse each of those.
What's the count actually holding up?
So there's a few times when we're gonna like want to look at one of the fields in one of these JSON objects, and it's not there, right? And so if we're not careful, we'll get like a key error. Any thoughts on how to handle that? So you can catch the key error. So you can use try catch. That's one approach. Any other ideas? So what I usually check for is that to make sure the key exists before I look at it. So I have a lot of tests that look like so if actor in object and actor equals. So you can check to see if the key is there with the in and then and it with the rest of your test. And so if the field is missing, you won't. So let's talk about the questions that we're trying to answer and how we're going to try to figure them out. So the first question is, which actor has been in the most movies? How are we going to go about figuring that out?
I made a data frame, and then I took the column that has actors in it, and I said for every row in that, parse out the list of actors, and then if they're not in a dictionary, add them to the dictionary, and if they are in the dictionary, add one, and then just go back and figure out who has the highest count.
Yeah, so we can keep a dictionary that maps actors, the number of movies they've been in. There's actually a built-in data type for Python. I think it's called counter, but if you Google Python default dict, that'll lead you there. And it's designed specifically for this purpose. Like if you look up something and it's not there, it sets the value to 1, and otherwise it increments it. So that's kind of a useful tool. All right, so we can just do kind of a hand-rolled Python analysis question, analysis approach. Right. What if we think about our data in a graph structure? So first off, how might we think about this as a graph? What would the nodes and edges be? Vector would be a node or an edge. So let's think about the first two questions that we want to answer. Who has done the most movies? And we're interested in 6 degrees of separation from Kevin Bacon. And how can we how can we think of our data as a graph to help with these problems? Maybe the Kevin Bacon one's more obvious. So we could consider having 2 types of nodes. So we could have a graph with mixed node types, with actors and movies. And what would the edges represent? What relationship? The actor was in the movie. Right, so that's one way we could approach it. That's a little, might be a little bit tricky because we have to kind of keep track of which node is which. For doing the 6 degrees of separation thing, we have to be a little bit careful. So how would we go about doing 6 degrees of separation? So I want to know like how Kevin Bacon is connected to Shia LaBeouf. How would I go about doing that?
Traverse your graph. Check, I guess, how many nodes you have to pass through before you
So what algorithm specifically, or what analysis problem is that we're doing there? It's not really a traversal. I don't want to look at the whole graph. Shortest path, right? And so that we could use BFS or Dijkstra, which would be the same here because we don't have weights. Okay? So we'd use compute the shortest path between them, right? If I have this weird hybrid graph of movies and actors, right, the number of degrees of separation is not exactly the length of the path, right? It's going to be like half that or something. Because to go from Kevin Bacon to the next actor, I have to go through a movie, so that's going to be 2 edges. Right? So I have to be a little bit careful if I came up with a graph like that. Okay? So there's maybe 3 ways we could think about it. We could consider the movies as nodes. Right? We could consider the actors as nodes. Or we could do a hybrid where we have movies and actors as nodes. With these graph designs, so we'll consider the case where we pick actors or movies. Let's go back to the first question. Which actor has been in the most movies? So which of these graph representations makes this a pretty easy question to answer? So if I have actors as the nodes, in terms of my graph data structure, what question am I asking? And what's the term for the number of edges for a node? The degree, right? So if I have actors as nodes, the actor that's been in the most movies is the degree of that node. Okay. So, and then the Kevin Bacon question is a question of shortest paths. Is a graph like this, is our data naturally shaped like a graph? Does this graph really capture what's going on in the data? Not really. What's weird about what we're doing here? So maybe let's look at this version. Where we have actors as nodes. That seems pretty normal, right? What's weird about this movies as edges thing? Yeah, a movie is actually a relationship between more than 2 actors. Right? So this is an example of what's called a hypergraph. Right? So a hypergraph is a graph-like data structure, except the edges connect as many or as few nodes as you want. So it's like less of an edge and more of like a webbing or something. And so this would be an example, probably better modeled as a hypergraph. But we can think about it as a graph where we have pairwise edges as well. Anything else that's kind of weird about this representation? Really label 2 actors here. I have Mark Hamill and Harrison Ford up there. Does this graph really capture their relationship? No, what's the problem? There's been at least 4 movies they've both been in. Okay. And so this is actually, if we're going to represent it with pairwise edges, this is probably actually what we call it multi-graph, where we can have multiple edges between the same pairs of nodes. So Network X does have a multi-graph class. I don't think there's basically any difference between working with it and working with the normal graph object, except you can have repeated edges added. Right? So if we represent our movies as this type of graph, then we can answer the first two questions pretty easily. So how can we take our basically array of JSON objects and turn it into a graph? Kind of tricky. So a nice thing about Network X is that if you add an edge and the nodes don't exist, it makes the nodes. So we can kind of completely ignore making the nodes, which is kind of nice. We can just think about the edges that are part of the graph. So how does the data that we have kind of correspond to the edges that are going to be in our graph? So this one makes, I would say probably this, we would make this kind of graph.
And all of the actors in each object.
So I'm looking at a movie, right? What edges correspond to that? What edges in the graph correspond to that movie? So I have Star Wars, right? Which edges are going to appear in my graph? There's an edge for every combination of actors. And that is the perfect word, because that is exactly the operation we're doing, right? We have the actors in our movie, and we want all of the combinations of size 2 of those actors. Right? So everybody remember commutations and permutations from whatever math you talked about. So combinations, we don't care about the order, so I don't care if it goes Mark Hamill, Carrie Fisher, or Carrie Fisher, Mark Hamill, right? And I need to pick 2 out of my set. In Python, there's in the standard library, there's a package called itertools. And in there's a function combinations. That gives you give it a list and how big the combinations you want, and it will give you all the pairs. That's kind of cool. So you can get all the combinations of size 2 of the actors, and each one of those corresponds to an edge. And so that's how we can make a graph from our data set. Okay. Any questions about that? So we'll stop there for today. We're going to keep working on this. So for tomorrow, do your best to answer the first 2 questions we have there. So which actor has been in the most movies? And is 6 degrees of separation from Kevin Bacon true? Okay. And then think about how you're going to answer the next question. So is there a comparable thing to 6 degrees of separation from Star Wars? And how would you go about trying to figure that out? Okay, so spend 10 minutes thinking about how you would answer that question and what code you might want to write. We'll talk about that tomorrow, and then we'll keep working on this. Okay. So yeah, try to answer the first 2 questions for tomorrow. Tomorrow we're going to start looking at interactive visualization techniques. So we're going to look at a JavaScript tool called D3, which is so the matplotlib stuff we've been doing is like pretty pretty limited, right? There's like a fixed set of things we can do. It's pretty wide range, but they're not really interactive, and there's like, you can pick from these, this group of visualizations we give you. Right? With D3, it's like, do whatever you want, but do it by hand. And so that's a very different kind of way of working with data visualization. We'll look at how we can include interaction in the mix and all that sort of stuff. So, all right. I will see you all tomorrow.